I'd like to tell you a little bit about my comet exploits, something that I recently did. I took a picture of not one comet, but two, in the same field of view. That is actually pretty rare. Certainly it's rare to have both of those comets being kind of similar in brightness. Here we have one comet, and it shows almost like a quintessential comet shape, with a head that's relatively bright and then a little tiny tail. Of course, it's probably huge, it's just far away. And then there's another one that doesn't have that much structure going on, kind of a diffuse ball, but two comets. Now, what makes this field interesting, at least interesting from an image processing point of view, is that the two comets are moving completely differently. They have different orbits. So you actually process the image, when aligning on the comets anyway, twice. You have to do it twice, one for each comet. Same data, but you have to do it differently. And I found that, of course, to be a very interesting kind of endeavor. So I would just like to point out a little bit more about the field, just so you can see. Unfortunately, the telescope I'm using is relatively small. So you have to zoom in here like 200% to see a little bit of the background universe, but it is interesting. Throughout the field, there are lots of galaxies. Some of these are actually quite famous, but here is just a group of galaxies. You can see a collision of galaxies here. There's some spiral galaxies running around here, and so on. I just think this is a really neat field. It has two comets. It has an interesting background canvas on it. The stars look fine, right? So I would like to point out a few more elements of what made this image kind of interesting in terms of overall processing. So let me begin by actually blinking the frames. That's going to be the first part, and it will inform people who may be unfamiliar with working with comet data and working with this particular situation, which might happen for other people. So I do want to highlight it just in that sense as a useful exercise in how to approach taking pictures of two comets at the same time. Now, I know the desktop is a bit of a mess here, and that's because this is a real project I was working on, and it became complex because I had two comets. Now, they weren't very big in the field, but I still had to do the same exercise to get everything to work. So let's load some frames. Now, I've always felt that there is a huge benefit to blinking frames. By blinking the images, it is remarkable what you can learn not only about the target that you're working on, but just in terms of astrophotography, in terms of image processing. Everything is there that when you blink the frames, you can see variations, and it tells you about the data, it tells you about astrophysical processes, it tells you about artifacts, satellites, everything by blinking frames. So I'm a big proponent of this. I'm going to go ahead and blink them, maybe not quite that fast. Let's see if I'm still blinking quite quickly here. So what I'd like you to notice is I'm not going to even zoom in yet. You can probably see this comet moving just a little bit here. But I'd like to point out something else. And again, I'm going to make this a more general talk, just so you can see the way in which I view images, right? So you'll notice that the left side of this image is brighter at half the frames, and then it's brighter on the right side of the image. There's a gradient on the left, and then a gradient goes to the right. By the way, these are all the green data. It's not that many frames, really. There's only 20 frames here. Why the gradient on the left and the right? What is that about? Well, there's a couple of things. This is a wide field of view image. I was using an astrograph that gives me a field of view that is 4 degrees on the longest dimension, and a little less, obviously, in the other dimension. And what that means is that, especially when you're looking low in the sky, but even in general, no matter where you're looking, the ground is on the bottom, and we humans who now live in a universe that is filled with light pollution. Light pollution generally has a gradient that goes from the horizon upwards in the sky. And when you take pictures with a telescope as I have that is on a German equatorial mount, when you flip across the meridian, what happens is the direction of the horizon is going to change in your images because I am now aligned on stars here, right? I've aligned on the stars, so the direction in terms of right ascension and declination is the same, but the direction of the ground is not the same. And that's what we're seeing the gradient flip, because the sense of which direction the ground is flipped as well. Now, you can probably, I'll zoom in here, you can probably see the motion of this comet is considerably more than the motion of this one, which is, of course, interesting. Now, these comets, of course, have names. This one being 2022, I believe it's E2 Atlas. Now, the other one is Swatchman. I can't even pronounce that name. I just call it SW, just to make it nice. But what I want to also show you is there's much more in this data. I'm zoomed out here, so it may be quite subtle. I'll zoom in a moment, but if you look very closely, right here, it starts there and it just zips across this frame. What is that? That is an asteroid, and very likely it is a near-Earth object because of its motion being so quick. Again, keep in mind these frames are, I believe these are 6-minute exposures. So every one of these frames is 6 minutes. So this is going across the sky in a few hours. And here it is. Now you can see it more closely. There it goes. Now what I want to impress you is that as I look around, the frame in general, you get the grainy appearance, and this is, of course, noise. Some fraction of this noise comes from the read noise that we get every time we download the camera. There's also just photon noise, if you will. There's just the fact that we're looking at a random process when we collect these photons coming from space, changes in the seeing. It's not very dramatic in this image, but you can see it. And yes, I know, look, there's another one. In fact, it may or may not surprise you that in this frame, just about everywhere I look, I'll be able to find something moving around. There are hundreds of asteroids in these frames. I know that there were some others down here towards the lower left. Here's one coming into the frame right here. And here are not one, but two more. Now, when we look at asteroids such as this, we're looking at a combination of motions. There's the motion of the orbit of the asteroid itself, but there is also a lot of this motion is due to the Earth moving around the sun in the course of, some odd hours here. So, these asteroids are all going to tend to move in a particular direction, especially if we happen to be looking in the opposite direction of the sun. And that happens to be, in this particular data, the direction I was looking at the time. Let me just scroll. Oh, before I leave this screen, let me point out one other feature here. There it is. If one of these frames, and I can freeze it. Why don't we freeze it on that frame? So we will come here, and there it is. Now we have a streak. Now the streak is not an asteroid. It's not a comet. It's only found in one frame. And most importantly, you'll notice that it's very pixelated. It doesn't look as if it is a formed image. So this is another very important part of astrophotography. When we take pictures of stars or galaxies, asteroids or nebula, everything we take a picture of has one of these. It's a point spread function. There is nothing smaller that you can resolve. A star is the smallest thing that's going to be in your data, in your images, and it is a spread of light. Now, it can be a very small spread of light, but it's always a spread of light. Anytime you see something in your frame that does not have that spread of light, it means it wasn't caused by light. It wasn't a focused set of photons that are incident on your sensor. So what is this? It's a cosmic ray. Cosmic rays are high-energy particles, generally coming from space, although you can have particles coming up from the ground as well. And they interact with electrons in your sensor. They move those electrons in the same way that light is moving the electrons. So we have a signature here. And there isn't necessarily a way that the sensor can distinguish between electrons that have been moved because something bumped into them, like a high-energy particle, compared to light being incident on the sensor and doing the same process. But we can distinguish them in the sense that it isn't it isn't light because it's not focused. It doesn't have that distribution that we get when we look at an actual formed source. So that's a giveaway. Now, there are also artifacts that are of this type as well. If I continue to blink, we will see that there are hot pixels that might persist in the data, although this data is pretty clean. I don't see many of those. I do see another very small little cosmic ray here. It just lit up a few pixels in one frame right there. But we're not done. There is more in this data. Here's an example of another asteroid, and like I said, there are literally hundreds of them, and this might not come across on the frame, but let me just show this to you. Here, if you look very closely, there is a very faint group of pixels. Let me see if I can do it again. There it goes. It starts here approximately, then it moves across. That's an asteroid. It's just at the faint limit of what is possible for this system to detect for a given period of time. And let me just then go back to a brighter one and indicate why that is, because this is another important concept. It is vitally important for comets as well as asteroids. It is that when we're watching an asteroid like this, what limits our ability to be able to detect it well? It isn't the exposure time, because the comet is moving. Since it is moving across our pixels, the length of time that it stays or sits on any set of pixels is the maximum exposure that you're going to get as far as the brightness of the asteroid. Because as it moves to a new set of pixels, we're no longer accumulating, gathering light on the same pixels. And that means that the appearance of these asteroids is being determined not by the length of my exposure, but by how fast they're moving. The faster the motion, of course, the less time on any particular pixel, and therefore it needs to be brighter to be able to see it at all. All of that comes into play when taking pictures of comets, just as we are doing here with asteroids. So this is a wonderful frame that shows us a lot about the solar system. Now there obviously are some man-made activity here. This is truly a satellite passing into the frame. It must have started in one of the frames, and maybe it was coming in and then the exposure ended or something along those lines. So that's why it's not going all the way across the frame, but it is a satellite. Now, how do I know that's a satellite? That's a formed image. That has a point spread function. That's light. Therefore, although it's not an astronomical object, it is something where we're reflected light, we're focusing that information on the sensor, and we see it as a real source, unlike, say, a cosmic ray or an artifact like a hot pixel. But let me show you just how fantastic it is when we look at the whole frame and label everything. So this is going to be an annotated version. I went through and annotated each frame with labels of what is in this field of view according to the catalogs that are available and by using PixInsight. I have a video which shows how to use the annotation process in PixInsight. Now, this is what the field looks like when you label everything. If I blink the frame, there's a lot to see here. First thing I'd like to point out is that ignore for the moment the the labels that are jumping around. I'll explain that in a moment. But in a very kind of general sense, there's a drift of everything in the frame going from left to right. Most of that is due to the motion of the Earth. Some of that is the motion of the asteroids as well, moving around the sun. Now, if we zoom in, we can see another element of what is going on here. Let's see if I can find one of the asteroids that we were looking at earlier. Okay, here's one, Laputa. This is a basically 16th magnitude asteroid. It is labeled here properly, although you'll find that it's not quite aligned. You'll see that there's a little bit of an error, and then it kind of gets better in terms of the alignment of a little precision, the astrometric precision. I suspect that some of this has to do with the fact that there is a fairly large distortion towards the edges of this frame of this very wide field of view from the astrograph. So optical aberrations, of course, distortion, non-flatness of the field are going to cause some astrometry errors, but in general, it's doing fairly well. Now, as this is a magnitude, 15.8, basically 16th magnitude, that tells us very important information. Given that speed, given this kind of general motion, what the faint limit is, not for stars, which is going to be fainter because they're not moving, but for the asteroids. This is another concept that's very important to appreciate when we look around the field of view. So let me just kind of randomly here go in the field of view towards some of these other asteroids, and we'll zoom in. We'll see a lot of them have, like here is a 17. This is almost 18th magnitude. I can see it there, right? This one right here, Wallach, asteroid, here, I'll move it over a little bit. So Wallach is detected. So we haven't reached the faint limit here. But by golly, when we're talking about a 22nd magnitude asteroid, there's no way we're going to see that at all. I can see this one here. If we go down a little bit, it says that it's at approximately magnitude 18. So it seems as though it's probably around 19th magnitude is going to be too dim. If you recall earlier, we found a really fast-moving one that was right at the basically the limit. And let me see if I can find that one again. I know it was near some bright stars. Let me find that. Well, I didn't find the faint one yet. I'll get to that limit, but I did find what is probably this one here. The astrometry, as you can see, is in error, but if you watch the label, it moves right along with it. So it's a fairly bright object, but it is doesn't look all that bright because it's moving so fast, right? And it would be interesting to look it up. So maybe we'll look up this number, 152.563. I'll just go ahead and note that. And we'll see if it is actually a near-Earth object based on its motion. Could very well possibly be. You never know. So 563, that's the kind of object that, for example, the surveys are interested in trying to find. So while I'm here, let me just point out the reason for the weirdness in the labels is that there is an algorithm that tries to avoid overlapping labels with either objects or other labels. So the algorithm is what's causing that strange kind of shifting that you see. If there are no collisions, there would be no problem, but that's just part of the algorithm for labeling. Just to show you, there goes the comet, which is kind of cool. Well, I found the one that I had pointed out earlier, but unfortunately it's near the left side of the, it's kind of near the left side here of the little marker. Makes it hard to see, but about 19th magnitude appears to be the limit. And these are 6-minute exposures. So in 6 minutes, you can see a 19th magnitude asteroid, basically with this small telescope, which is, pretty good. Now, what I'm doing here is this page is the Horizons page, which I talk about in other elements of Comet Academy. Very useful. It has a small body database lookup, so we can now look up that asteroid and we can learn a little bit more about it. The one that was moving kind of fast, I predicted, and let's see if it's true, that's probably a near-Earth object. Just based on its rate of motion, and look at that. It is a near-Earth object. It is an Aten, that's the type of asteroid. And looking at the Wikipedia page, very interesting. These are asteroids that are interior to the Earth, in its orbit about the Sun. And they are, they're Earth-crossing asteroids. These particular asteroids only account for 7% of the known near-Earth asteroid population. It's pretty cool to actually see that particular one in the data. I guess this graphic here kind of gives us a sense of what an Aten does as the Earth orbits the Sun. Very, very cool. I do suspect that some of these could be potentially hazardous. So in looking up the information, we can also see information about the discovery, where it was discovered, when this was discovered at Palomar back in 1992. All kinds of interesting stuff. And then if we loaded up the orbit diagram, we could actually animate the orbit of this particular asteroid. So now let me show you just a few more items about the construction of this image of these two comets. The first is, of course, as I mentioned, I had to use comet alignment to produce comet-only images, comet masters, only masters, of both comets. So I aligned on this one here, and you can see after, of course, removing the stars, what we're left with. The background, by the way, is very textured-like, and that's because these comets, they weren't really moving very quickly. That means that there's not a whole lot of rejection that happens. When you have large spaces in time with the motion of the comet against the background sky, stars and other things will be rejected and will go away. Unfortunately, that's not the case with these comets. So we're left with this, and you can see the motion here was greater. You can see more of the smear of kind of that noisy textured background. But two comets, two images. Now, once we have these together, we create, I just screen blended them basically. Now, of course, I'm going to permanently stretch the image, and then I blend them together to produce this kind of image. I also needed to do a color correction, though you can see, because I'm putting two images together, it gets a little wonky, it gets a little crazy, because they both have backgrounds, right? I have a background in each of the two comet images that I'm putting together. But ultimately, you get the idea. We get an image that has two comets in it. Now, although I had to align them separately because their motions were different, I chose the same reference frame for all of it. So in time, for this particular reference, this is the position. I wasn't being arbitrary here. These two comets were in this position at a particular moment of time. And that's because of the reference frame I chose. I chose it to be one frame for both alignments. And then at the end of the day, I try to blend the two images together in such a way, and this is a technique that I just recently tried to develop, so that I can get rid of all of this. There is using the new image blend script, I can take these two images and do a better job than just screening them together like this. If you just screen them together, you get kind of a mess. So there is another method that will take advantage of the fact that the motions of these two comets are different, so the background is different, and you try to basically threshold it in such a way that we're just getting the comets, at least as much of them as we can, and then, of course, you do the final blend, which is to put them in the frame with the stars only data. Now that still needs to be cleaned as well. On this particular frame, I did not try to subtract the comets. You might wonder, did I subtract twice? No, I didn't bother to do it. It just wasn't necessary. These two comets were not moving very fast and they're very small. So they made, in my stars only data, well, that is on the star line data, when I integrated those images, the comets partly reject. They're still there, but they're partly rejected. So all I did is I separated the stars out, used the clone stamp tool just where the comets were, because there are galaxies in here. I didn't touch those. But just where the comets were, I just went and got rid of them in the stars only image, the remnants of them anyway. And then I had a stars only image that I blended with the comet only image to get this final result. I hope you enjoyed this. This is the kind of thing I can do, extemporaneously, to just talk about what's in the data, what's going on about fate limits, motions of asteroids, different kinds of asteroids, looking critically at the data, looking critically at the astrophysical phenomena, and putting it all together in a story that makes for a complete astrophotographic experience. I hope you'll join me again in more of these videos which describe the universe around us.